Thank you very much, son. So before I start, let me remind you that you can ask questions anytime, as much as you like, and that you're, of course, also welcome to post questions on the chat or to raise hands, but you can also just shout out. If you post questions on the chat, be aware that I may not see them immediately, so you may have to shout out if I don't react immediately. Okay, so maybe let's start the lecture with a short review of what we have seen on Monday. So I remind you that the purpose of the lecture is to study, well, the final goal is to compute Feynman integrals or scattering amplitudes beyond tree level, which means that you have to do loop integrals, you have to evaluate loop integrals. And the goal is to understand the class of functions that shows up when you compute these integrals. Now, in general, we don't know what class of functions we get when we compute loop integrals. So we focused here on the simplest class of functions that we know shows up, which are these functions which we called multiple polylogs, and I abbreviated them MPLs. And so I remind you that they were defined as iterated integrals, an integral from 0 to x, and then you have the same, in the integrand, you have the same function, but with one index less. And the number of these indices, we called it the weight, the number of integrations. And the other thing we saw is that there's a special case, which is, well, the log, which is just the polylog of weight 1. And there's also, say, the dialog, which is also a special case, trilog, and so on. So those are the quantities we looked at. So what did we say about them? Well, the first thing we said is they form a shuffle algebra. And we said, well, this is called a shuffle algebra because it is actually the algebra that corresponds to shuffling cards. I remind you the basic example being GAX times GBX is GABX plus GBAX. And then we said there's also some Hopf algebra structure, which means there's co-product, and then in the end, we said, well, you should look at something slightly more general, which is called a coaction, but let's do not go into this distinction here. And we said that, well, that is an operation which we call delta, which takes one element in my space, vector space A, which is my space of all polylogs, and gives me something which is a pair. And we looked at some examples. We looked at, and there's in particular the following properties: that it is linear with respect to Q, or algebraic numbers, Q bar. And it maps a product into the product of the tensors. And we also said it's co-associative. Which means that there's a unique way of, so you first split things into 2, but then you can split things into 3, and so on. And this iteration is unique. There's not, I mean, if you go from here to here, there's a choice you have to make. Do you iterate in the first slot or in the second? But as we said, it doesn't make a difference. And we also looked at some examples. We said delta of log x is delta is 1 tensor log x plus log x tensor 1. And we also looked at a very general formula for Ln of x, which is 1 tensor Ln of x plus Ln of x tensor 1 plus sum from k equals 1 to n minus 1, Ln minus k of x tensor 1 over k factorial log to the kx. The formula is more nicely written on the slides. I will share the slides at the end of the lecture. And it's recorded. And then the last thing we saw is that, well, for x equal to 1, Ln of x becomes a zeta value. So remind you that zeta 2 is pi squared over 6, zeta 4 is pi 4 over 90. In general, zeta 2n is proportional to pi to the power 2n. This is only true for even weights. For odd weights, no such relation is known. And we said that we actually need that delta of pi has a special role. Pi is only in the first entry. So that actually we said that here in the second slot, there's some more symmetry. In here, the second slot, I should always work modulo pi. Not in the first, only in the second. This is something we saw at the very end of the last lecture. Okay, that was a lightning review of what we saw on Monday. Before we go on, are there questions about this?
Claude, do you always have the last an not equal to 0 in your definition?
Yeah, so I gave here a short definition. So yes, here an should be strictly speaking non-zero. If you have g, if the last one is 0, so if you're all 0 essentially, you can always use to this, it's 1 over n factorial log nx. Thanks. More questions? Okay, so then let's go back and study the coaction in more detail. So we have now this operation that allows me to take a polylog and to break it into a pair of two simpler objects, where simpler means a pair of objects of lower weight. So that's something that was already asked last time. So for example, we saw last time that for the dialog, delta Li2 of x was actually 1 tensor Li2 of x plus Li2 of x tensor 1. So those are the two trivial terms that are always there. And then there was the only non-trivial term was the one where you break it into two terms of weight 1, which has this form. And you see that, well, it's something that was asked already last time. So why is it log 1 minus x log x and not log x log 1 minus x? Is there a reason for why you break the symmetry in this particular way? And the answer is yes, there is, and that's what we're going to explain now. And no surprise, it's going to be tightly linked to the way the symmetry was broken for pi, that pi has this special role. Okay, so to understand that, let's go and do something else. Let's first go and compute the coaction on the derivative of the dialog. Okay, so I remind you that Li2 of x as an integral looks like this. That's the integral definition of the dialog. So you can easily evaluate the derivative with respect to x. It's not a big mystery, it gives you this. Okay. Now you see here that this factor here that is a rational number. So if x is a rational number, then 1 over x is also a rational number. And we said that delta is linear with respect to rational numbers, so I can pull out 1 over x and also the minus sign. But now I have delta of the log, which I know how to evaluate. Okay, so I get the coproduct of the derivative. Okay, fine. Why do I care? Well, you see, that is now, here you see what is left over is precisely log 1 minus x, which was precisely what we said is the thing that sits here in the first entry, not in the second. And yet, so what happened to the log x? Well, the log x, you see, that is precisely what sits in front, or rather, what sits in front is the derivative of log x. So there you see what happened to the two entries. One of them represents the derivative, and the other one represents what is left of the derivative. So in other words, I could do the following. I now compute the coproduct of the dialog, and then I do this weird notation here, which is just saying I act with this, with the identity on the first entry, and I act with this guy on the second entry. So let me maybe write it explicitly. When I have something like two functions f and g, and they act on its tensor fb, what I mean by this is f of a times g of b. Okay, so it's a very natural thing to do. And so what this simply means is I just differentiate now in the second entry. So what I'm going to do is I just going to act with this derivative in the second entry, and only in the second. And well, you can easily see that you get this. You actually, and now from there you see that this is in one-to-one correspondence to the terms, to two terms that you have there. And I see that I made a typo. I apologize for that. Here it should of course be 1 minus x. And also here. I apologize for that. So then you see these two terms are in one-to-one correspondence. They look slightly different simply because, well, this is a rational number. I can move that in or out of the tensor product. That doesn't matter. I can move it in or out. So that is in the same here. I can put this guy either in the second slot times 1, or I pull it out and I write it in front as I do here. Okay. So you see that taking derivatives is the same as computing the derivative only in the second entry. So this tells you what the meaning of the second entry, the rightmost factor in the correction, is. It encodes the derivatives of the function. So in formulas, this just summarizes what we just said. If I first act with the coproduct and then I take a derivative, it is the same as, sorry, I first take a derivative and then I act with the coproduct. It's the same as first acting with the coproduct and then taking the derivative, but only in the second entry. That is what is written in red. That is what you should remember. Derivatives always only act in the second entry of the coaction. You can be slightly more general. You can actually say last, because I could now have an iteration into 2 slots, 3 slots, and so on. It will always act in the last entry.
Can I ask a question?
Yeah.
So just to anticipate, so are these related to cutting of diagrams and so on?
That is tightly connected. So if you translate this to cutting of diagrams, So this is the second entry in the co-product that contains the cuts of the diagram. And you know that the cuts of a diagram satisfy the same differential equation as the full diagram. That is what is encoded here. It's the fact that if, well, it would take too long to explain this, but if you...
Okay, thanks.
Okay, good. So now you can ask, what is the first entry? The first entry, well, if you think about it, you have polylogs, which are integrals, and they have discontinuities. There are essentially two natural operations you can do on them, right? One is they're integrals, so you can differentiate them, you can remove integrals. And the other operation that you can do is, well, they are multi-valued functions, you can take discontinuities. So you have two entries in the core product, you have two operations you can do. The derivative, which is one of these operations, acts in the second entry. Well, it's not surprising that the other operation you can do acts on the first entry. So this tells you a bit what the meaning is of these two entries in the co-product. You have two natural operations you can do on a polylog, taking derivatives and taking discontinuities, and that is precisely what is encoded in the two factors of the co-product. Now, I didn't not yet define precisely what I mean by this taking discontinuities. We will do that now in the next slides. But what I want to say here is, well, I guess you all know, at least intuitively, what it means in discontinuity. You all know, for example, that the discontinuity of the logarithm is 2 pi r. We will review that on the next slide in case you don't remember it in detail. But the discontinuity of the log around x equals 0 is 2 pi I. And I would like to highlight here the following. Remember that we had this special rule for pi. Pi only acts in the first entry, not in the second. Well, in the second, you have to work entry of the core product, you have to work modulo pi. It's not a surprise that you have precisely discontinuities act in the first entry, and pi is only present in the first entry, because every discontinuity is proportional to pi. Every discontinuity of a polylog is proportional to pi. So the fact that you had this special rule for pi is actually a direct, well, it's hard to say what is the consequence of what, but it's intimately linked to this relation here. You see, it has this relation is the same as symmetry as this special rule for pi. Okay. So as I said, if you don't remember exactly what discontinuity means, we will review it now in the next slide. So maybe let's first review what this equation means.
Sorry, Claude, there's a question in the chat.
Yeah. Isn't this condition derivative in the last entry? It satisfies because of the fact that you find del ln x to be anti-symmetry. Well, it explains why I had to define it so. Had I defined it here with these two swapped, sorry, then of course these relations wouldn't hold. So you can say, yeah, it's a consequence because I defined it this way. Well, first of all, you have to know that this is part of a much larger mathematical theory where all this comes out naturally. There's only one way to do it. The other thing which you should now keep in mind is that there was also this special rule for pi, that you should work modulo pi everywhere except the first entry. So it's all interconnected. There's only one way you can do it such that all the relations hold at the same time. Now, of course, you can decide to swap left and right in all formulas, and it would still be the same. But up to, say, a trivial swap that you would swap left and right in all formulas, there's only one way to do it such that all the formulas hold at the same time. So it's not a consequence of defining it this way. It's something which is actually a consequence of a much larger theory. And there's only one way to do it such that you get the right answer. Otherwise, you will get some formulas right, and then you end up with some contradictions later on. Does this answer your question? Okay, I don't see an answer, so I assume that answers the question. So maybe let's briefly review what we mean by discontinuities. So let's take some analytic function f. So what do I mean by discontinuity of f around the point x0? Well, I have an analytic function. I can analytically continue it. In particular, I can take a little path that goes around the point x0. So I start from the point x, I move along, actually go here. Let's look at the example of log x. And let's take log the x0 to be 0. You know that there's a branch cut and on the negative real axis. So what I do is I start from some point x, and I move around x0 equals 0. And then I go back to x. Now, as you see, I crossed the branch cut now. So when I go back to x, the value of the function has changed because there was a branch cut. I crossed the branch cut. And what I mean by discontinuity, I mean that, well, if I denote by f with this little circle, what I get when I move along this path that goes around x0, and I go back to x, and then I compare it to the value that I had at the beginning. So I compare the value that I get at the end of the analytic continuation, the value I had at the beginning. And that is the discontinuity. Now, if there's no branch cut, the value will not change. If I go back to x, I get back the value that I started from, so the discontinuity will be 0. But if there is a branch cut starting at the point x0, then after analytic continuation, the value of f at point x will be different, and so the discontinuity will not be 0. Okay? So let's go back to the example of log x. So then I think this becomes very clear. So I started at the point x, and then I moved along this path, go back to the point x, and well, I compare the value that I get for log x before and after analytic continuation. Now, before, that's what I have. This is before. And after, that's what I have. If it's after, the value of the argument has changed by 2 pi I, because I move along a circle around the origin. So the only thing that changes essentially is the argument of the function. Well, the argument of x, phase. And it changes by, well, moving by a whole circle, so by 2 pi I. And so if you now evaluate, so after you get this, sorry. And so now you can see, I guess you can easily see what happens. This gives you 2 pi I, because the log of the product is just the sum of the logs. Log x cancels, and the logarithm of e to the 2 pi I is 2 pi I. So the discontinuity of the log is 2 pi I. Now, what would it be for the dialog? Maybe I think it's an instructive example to see what is discontinuity of the dialog. The dialog has this integral representation. It is defined as the integral from 0 to x, right, of some integrand. So let's compute the discontinuity around 0? Well, I have to start from the point x and move around to point 0. I'll go back to x. So the discontinuity around 0 will be what I get by integrating along, well, the original path is 0x, and the new path is actually, well, 0x, and then you go along the yellow path. So it's the two things combined. The difference is, of course, well, that the contribution from the straight line 0x goes away, and it's just left with the integral along this yellow circle, which is nothing but the residue at t equals 0. There's indeed a simple pole at t equals 0, but log 1 minus t vanishes at t equals 0, so the residue is 0. So the discontinuity of the dialog around 0 is 0. However, you see that there is in the integrand, there is this log 1 minus t. So something happens when t is equal to 1. So you can also go and evaluate the discontinuity as you change x along a little circle that goes around 1. And I invite you to do it as an exercise, so we can do it later at the end of the lecture if there's time, and to find a solution here. If you do it, you have to play a bit with Polylogs. You have to find a better integral representation where, in the end, you realize that the discontinuity of the dialog around 1 is 2 pi I times log x. So that's here. You can go through this little exercise calmly, and you get to the conclusion that the dialog has a branch. This means that the dialog logarithm has a branch cut which starts at x equals 1, goes off to infinity, and when you cross this branch cut, you change the value of the function by 2 pi I times log x. And the minus sign counts whether you cross the branch cut in the clockwise or the counterclockwise direction. Okay, so there's someone asking, how is disk defined in case of multiple branch cuts? I can always do the same thing. When I could have another branch cut. So there's, for example, there's now clearly a branch cut here. There could be another branch cut somewhere here. And you see, analytically continuing along a little path, I can always do it in such a way that I just cross one branch cut at a time. I can always arrange it that way. Well, let's restrict to that case. So what I told you here, you can do it one branch cut at a time. There is a more general theory. Now, if you say, well, what if I were to analytically continue along a path that crosses two cuts? This can be done. Then you really get to some more involved mathematics. You talk about the monodromy group. But here, think of it as if you have more than one branch cut, you continue along a path where you just cross one branch cut at a time. Okay, good. So we said here now, well, I left it as an exercise. The discontinuity of the dialog around 1 is minus 2 pi times log x. So let's see what the coaction would give us. Well, if I act with the coaction on the previous formula, that's what I get. The coaction of a product is the product of the coactions. And now remember that delta of 2 pi I is 2 pi I tensor 1. Delta of log x is this. And so this is what you get. I remind you that A tensor B times C tensor D is A times C tensor B times D. That's what you need for the last step. Okay? Because this times this is this. And this times this No, sorry, it's the other way around. I apologize. This times this is this, and this times this. Okay. So, but what would I have gotten if I had computed the coaction of the dialog and I only acted with this in the first entry? So now I act with this, but only in the first entry. Well, clearly, disk of the constant function 1 is 0. So that term vanishes. But disk of d2 of x, we have it in the first line of this line, it's just minus 2 pi I log x. And disk of log of a log is 2 pi I. And so you see, you find indeed precisely the two terms that we found before. So this is an illustration of this relation that says discontinuities only act in the first entry. Okay? Other questions? This summarizes this item on the agenda. To recap, what you should remember is that discontinuities only act in the first entry of the coaction, derivatives only in the second, or in the last. Are there questions about this? No questions? Okay. So then we move on. And let us discuss something which some of you may know, some of you have worked with it possibly already, which is the notion of symbols. And as we will see, that is actually just, it's, if you want, a simplified version of the coaction. Simplified in the sense that it's easier to work with it, but you lose information. It captures less information. So to recap, remember that the coaction allows you to decompose a polylog into polylogs of lower weight. So you may, for example, take the dilogarithm, which has weight 2, and you decompose it into 3 terms. The first term has weight 0 in the first slot, weight 2 in the second. The second has weight 2 in the first slot, weight 0 in the second. And the third term has weight 1 in each slot. Okay. I can do the same for the trilog. Li3. Li3 has weight 3. I decompose it now into a sum of 4 terms. You can get this expression from the general formula for the coaction of the n that I gave you. One term has weight 3 in the first slot, weight 0 in the second. The second has weight 0 in the first, weight 3 in the second. Then weight 2 in the first, weight 1 in the second, and weight 1 in the first, weight 2 in the second. Okay. But now I can do the following. Remember, I can now, if I can break something into 2, I could break it into 3. So what we've done is we started from weight 3, and we've decomposed it into pairs such that the total weight is 3. By total weight, I mean the sum of the weights of the individual terms. But I could now go on. I could now, for example, take the weight 2 term in the first entry and decompose into a pair of weight 1. I would get 3 objects, each of which has weight 1. I could also have done the same starting from the weight 2 term in the second slot. But remember, there was this property called co-associativity, which tells you that the iteration is unique. So this triple object here, weight 1, weight 1, weight 1, is unique. We will see what it actually is in a second. So what you see is that there's essentially, whatever you do, there's a unique way to decompose an object into its elementary building blocks, which are all of weight 1. And that is true at higher weights as well. For example, if you have weight 4, you act with the coaction, you get 5 different types of terms: weight 4 and weight 0, weight 3 and weight 1, weight 2 and weight 2, weight 1 and weight 3, weight 0 and weight 4. And now you have pairs of objects, you can make them triples. There are different ways you could do that. For example, you could do it starting from the first entry and breaking things in the first entries into pairs. So weight 3 would become, the weight 3 here would become weight 2 and weight 1, and weight 1 and weight 2. While the weight 2 term here would become weight 1 and weight 1. Or I could have done the same starting from the second entries, where now here the weight 2 would become weight 1 and weight 1, and the weight 3 becomes weight 1 and weight 2, or weight 2 and weight 1. But again, because of coassistivity, the result that I get will always be the same, whether I iterate from the first or from the second. Now I can go on. I can now iterate more. I can now take the weight 2 that is in one of the slots and iterate it. But whatever I do, whatever way I follow, after I've broken it down to the elementary building blocks, the answer is the same. So there's a unique way of decomposing a weight 4 object into a 4-fold tensor of weight 1 objects. And I guess you can easily see from this argument that this will always be the case. If you start from a weight n function, there's a unique way of decomposing that weight n function into an n-fold tensor of weight 1 objects. And this quantity is called a symbol. So one way of defining the symbol is, it is the parts of the coaction we have broken down everything to a maximum. So the part of the coaction is 1, 1, 1, and so on. It has weight 1 in every slot. And we've also seen that it's unique. So there's a unique way of that object symbol. So the symbol, you can think of it as some kind of invariant attached to a polylog. It's a unique invariant that you can attach to a polylog. We had one invariant which was the weight. So here's a bit more refined invariant, which is called the symbol. For example, the symbol of log x, well, log x is weight 1, so there's a unique way of breaking weight 1 into weight 1, which is just you keep the function as it is. The dialog has weight 2, and if you look at the form of the coaction for the dialog, you see that the part that has weight 1 in each slot is precisely minus log 1 minus x tensor log x. And if you do it for Lien, it would be the generalization of this, which is minus log 1 minus x, tensor log x, tensor log x, tensor log x, and so on. Now, for notational reasons, you can see, since these, by definition, the symbol has weight 1 functions, so logarithms in every slot, you have log, log, log in every entry. So it's conventional not to write the log symbol. You just write down the argument of the log. But it's useful to keep in mind that where it actually came from is the coaction. It's literally always a log in front of everything you do. And all the properties that you get, and when you hear people talk about symbol calculus and the properties of symbol calculus, it all comes from the coaction, from the fact that there were logs. So for example, what are the properties of the symbol map? Well, they're just inherited from the coaction. So, for example, when you have a product inside one of these tensor products in a symbol, it is just the sum of the two entries. For example, you have here product, this becomes the sum. Why? Well, because underlying it, it meant actually there was log A times B, which become log A plus log B. The other thing is log of 1 is 0. So you just can remove all entries in the symbol that are 1. You can even remove those that are -1, because remember, pi had this special feature that you can put it to 0 everywhere but the first entry. So whenever you have -1 as well, -1 is I pi, you can always put it to 0. So whenever you have in a symbol plus -1, you can just drop these terms. The other thing is you also drop all zeta values. Why? Because we have seen that the correction on zeta n is this, say n is odd. But you see, the term, there are only these two trivial terms. You cannot decompose zeta n in any non-trivial way. So the symbol, which would be the piece of the correction where you decompose it only into logs, is 0. It's not there. There you also see one of the shortcomings of the symbol. You lose quite a lot of information. In particular, you lose all the information of terms that are proportional to pi squared, zeta 3, pi to the 4. So you lose a lot of information. It's very easy to work with the symbol because it has these very simple rules that products become sums, can drop all terms that contain 1. But at the same time, it loses a lot of information, particularly all the terms that are proportional to zeta values. The last property, yes?
Yeah, so when we considered this coaction and we arrived at this form with log 1 minus x times log x for lead 2, for example.
Yeah.
I think what we used was that the coaction should be consistent with the with differentiation, and then probably if we had like other combinations, it wouldn't be consistent. So if I have some, I mean, what I mean is if we had the symmetric combination, probably that wouldn't be consistent with the with differentiation. Is this true in general? I mean, if I have some functions on which I'm trying to define a coaction, should we look for like consistency with the derivative, or does it change in each case?
No. So as I said, the coaction here is just a special case of something much more general and much more abstract, sometimes called the motivic coaction in the mathematical literature, which works for all kinds of objects, not just polylogs. And it always has the property that derivatives exist in the second entry and discontinuities in the first.
Okay. I see.
So, so that property is always true. Here I just showed it in the special case of what happens when you act on polylogs, but it is actually done. And then there's indeed a unique way that you can do it so that you get consistent answers for everything.
Okay.
And if you want the reason that there's a unique way of doing it so that you get consistent answers for everything, is that this is just a special case of a much more general theory where you have no choice what you could do.
Okay, great. Yeah, thanks.
Someone asked in the chat, the symbol used for symbol is S. Yes, maybe that's my poor handwriting, but the symbol is a calligraphic S. Good. So the last property I want to mention is what happens when you compute a symbol of a product. So the symbol map is linear, S is linear. But what happens if you have a product of objects? Well, it turns out that what you get is the shuffle of the symbols, the shuffle product of the symbols. For example, the symbol of log x times log y. Well, the symbol of log x, we said here, the symbol of log x is x. So the symbol of log y is y. So what is the symbol of log x times log y? Well, it is the shuffle of the symbols. And the shuffle of x and y is xy plus yx. I'm not going to prove this formula. You can actually prove it. But it's always true that the symbol of a product is the shuffle product of the symbols. Okay. Are there questions up to here? So there are two more nice properties. So we also said these are just immediate consequences. So imagine you have a symbol S of some function f, which is this. We said that for the coaction, discontinuities only act in the last entry, in the first entry. So the symbol of a discontinuity only acts in the first entry. And now remember that this A1 is actually log A1. So we also said derivatives only act in the second entry of the coaction, and maybe let me again add here last. So the coaction usually we only have two, so second and last is the same. So here, when you compute the symbol of a derivative of a function, it is the same as computing the derivative only of the last entry. Where again, you have to remember that an actually means log an. Okay? Those are just the generalizations of the formats that we had for the coaction half an hour ago. And the reason I'm telling you this is because if you're only interested in the symbol, this last formula for the derivative usually gives you a very convenient way of computing. So someone asked, the derivatives only act in the second entry. Can this be generalized to higher order derivatives? Yes and no. So imagine you want to compute the So someone asks, can you do it for higher derivatives? For example, is this what you're asking? Yeah, okay. So, well, this means that, yeah, so what does it mean? You have to be a bit careful now what it means, because the second derivative will act on, well, let's maybe take an example. That's maybe easier. So the symbol of Lie3 of x minus 1 minus x tensor x tensor x. The first derivative of Lie3 is 1 over x times Lie2 of x. And the symbol of this is 1 over x times the symbol of Lie2 of x. And this is minus 1 minus x tensor x. And this is d over dx of log x. So this log x is here. And this guy is here. So the first guy, for the first entry, it works. But now if you take the second derivative, what do you get? Well, sorry. Well, you have to look at this. You have now to take this derivative of this, which has two terms. One term would be like this. And another term would be like this. Now, you see from here, so this bit is, so you get Leibniz rule essentially. So you get one term where you chopped off the two guys here. Each of them gives you 1 over x, and you're left with log 1 minus x. But you have the other term where you just chopped off the first two, which comes from here. But you get the derivative, the second derivative of the last entry. But this is here. Okay? So if you take more than one derivative, you have to take into account that the first derivative already produces some prefactor, and you also have to differentiate that one. So yes, you can generalize this formula, but it doesn't look as nice anymore. Does that answer your question? Okay.
Hi, could you say something about what does a symbol mean for the diagrams?
For which diagrams?
For say Feynman diagrams, if I have a loop calculation and n-order loop calculation, and I'm calculating the symbol for that answer, what is it?
So we will see that in the second part of the lecture. So far, we're just studying the properties of these functions. So far, it has nothing to do directly with amplitudes. These are just the functions that you get when you compute.
And okay, thank you. And another question is, like, in the conclusion of the last slide was that I could naively use the Leibniz rule when I have multiple derivatives on the symbol. Is that right?
Yes.
Thanks.
So what I want to say is that this last formula often gives you a more convenient way of computing the symbol. Why? You actually get a recursion. And the reason is as follows. Imagine you have a function for which the derivative takes this form shown in blue. The derivative of a function of weight n, I say, is the sum of terms. Each term has a function of weight n minus 1. And the derivative of a log. And I do not write derivative anymore. I write now the total differential. So the total differential of a log. The total differential, like so, 1 over x is for dx. 1 over x, for example, is d log x. So imagine that I have a function which has this property, a function of weight n, whose total differential is the sum of terms of weight n minus 1 multiplied by d log. Then the symbol, you can just read it off recursively from there. The symbol of this function fn will just be obtained by computing the symbols of the functions of lower weight and appending the argument of these d logs. You can take it as an exercise that you can show that this recursive formula in red and blue is the same as saying that this last identity must hold. So if you can compute the derivative of a function, you can reconstruct its symbol. And this can be a very convenient and quick way of computing the symbol. You cannot say, well, if this is so convenient and quick, why did we go through all of the gymnastic with the coaction? Well, the coaction is more general. Remember that the symbol loses information. It is an invariant that characterizes the function, but it loses information. So the coaction contains more information. But depending on what we want to do, maybe you don't need all the information. And then maybe computing just a symbol is easier. Okay, one other thing I want to highlight here, a function fn that has this property that it satisfies the differential equation of this, well, like shown in blue, is sometimes called a pure function. It's something that will come back later when we talk about amplitudes, and something you hear often in the context of scattering amplitudes is this notion of pure function. It means that the function has, so a pure function of weight n is a function of weight n which has a total derivative that involves only pure functions of weight n minus 1 and d logs. Okay. So let's just look at an example. So we know, for example, lead 2 of x is this definition. Now, I could go and compute a symbol from the coaction. I can also just go and compute the derivative of the dialog. The derivative is easy because it's an integral. You can easily get it. And so I get this term here, which is the first entry in the symbol, and the d log, which is d log x. And therefore, the symbol is just minus 1 minus x times x. So I can, in this case, I can easily get the symbol just from knowing the definition of Lie2 and the derivative. And you could construct the symbols of all the Lie ends in this way, but only the symbol, not the correction. Well, not easily. Okay. So that's all I wanted to say about symbols. Are there questions before we move on and discuss some applications related to amplitudes? Okay. Don't see any questions in the chat. I don't see raised hands, so I guess we can move on. So, in the last part of the lecture, we will now finally discuss applications of all this formalism. Those applications that come really from amplitudes. So the first application is, imagine you compute some amplitude, some loop amplitude, and you get an answer. Now, how can you massage this answer? Maybe you can simplify it, maybe you can bring it in a different form. In general, you would know. In general, you would have a huge bunch of polylogarithms and you wouldn't know what to do. So it's a bit like, imagine, well, remember your times in high school when you did exercise classes with sines and cosines. If you know there are all these relations among sines and cosines, which allow you essentially to write even a simple expression in the most horrible and complicated way. And it's the same here. So it may be that the thing that you computed is very simple, but you would need to know all the relations among these functions in order to find it, which in principle, in practice, you don't know. So the question is, how can you find these relations among these functions, in this case, polylogarithms, not sines and cosines, that was in high school. How can you find these relations among these polylogarithms? And how can you actually prove them? Or how do you know how to get them? How do you know they are correct? As we'll see, the coaction helps here a lot, the symbol. But before you start, you need to know one important thing about polylogs. So one important thing about polylogs is, and it's a conjecture, there are no relations among polylogs that have a different weight. So if two polylogs have a different weight, there's no way you can write one in terms of the other. It's never going to happen. I insist this is a conjecture. Mathematically, this is a conjecture. No one doubts this conjecture to be true, not even mathematicians, but it's not been proven that there cannot be a relation that allows you to write the dilogarithm as a sum of logarithms.
I have a question.
Yeah.
So if I just go on to evaluate it at specific values like x equal to 1 and so on, wouldn't it end up showing just like transcendentality of pi or something? Because
sorry.
So the evaluating this polylogarithms at specific values were giving us zeta ends and so on.
Yeah.
And they are like higher powers of pi.
Yeah.
So wouldn't like a simple proof be like, okay, pi is transcendental and if I can't sum.
Yeah. So pi is transcendental. That's correct. Now, can you, however, exclude that? How to say it? Okay, maybe the dilog and the log is a bad examples, but say the trilog to write in terms of logs. there you would get zeta 3. You don't know if zeta 3 is transcendental.
Okay.
So maybe weight 2, where you only have pi square special value, is a bit too special. But already, if you go to weight 3, you know that zeta 3 is irrational, but you don't even know if it's transcendental. And if you go to weight 5, where you have zeta 5, for all we know, zeta 5 could be a rational number.
Okay, thank you.
Okay, that is actually why this argument in red here is the conjecture, precisely because of these things. Even if you go to weight 3, zeta 3, we don't even know if it is transcendental. And if it's not transcendental, then of course all of these things about weights don't make a lot of sense, because then if zeta 3 is not transcendental, it would have weight 0.
Sorry, Claude.
Yeah.
You mean we don't even know this zeta value being irrational?
Not all of them, no.
Oh, I see. Zeta 3 we do know, but not
Zeta
higher
3
order
was,
zeta value.
yeah, zeta 3 was proven by a priori to be irrational.
Yeah.
But not transcendental. And as far as I know, even zeta 5 we don't know. There are statements of the type, like among the first, what do I know, many zeta values, at least one of them must be transcendental or irrational. I forgot the statement. There are statements of this type, but there's no statement that says definitely not transcendental, but also in general not irrational.
Thanks.
I insist, no one doubts that they are all transcendental. It's about what is proven and what is not proven. But I think for all practical purposes, we can always assume they're all transcendental, and that there's no relation among polylogs of different weights. So, well, let's take an example. Let's imagine you compute a loop integral and you get this expression t. It's a Duhr logarithm and a product of two logarithms. And you can ask yourself, can you simplify this? Now, well, if you may know the identity, you may not know the identity. But let's say you don't know the identity. What could you do? Well, you don't know. So the best you can do is that you say, okay, let's use the coaction and break it into simpler pieces. And maybe for the simpler pieces, I know the identity. Right? So if you don't know it for the full object, look at the pieces. So compute a coaction. And here I use a notation that is very common, very useful, but just that so the part of the coaction that has, like, say, weight P1 in the first entry, weight P2 in the second entry, and so on, I denote it by this. So for example, T here has weight 2, and remember that the coaction would always have this structure delta of T is 1 tensor T plus T tensor 1 plus something else. These two terms never carry any information, because those would be the terms that have weight 0 and weight 2 and weight 0. They do not carry information. The piece that carries information is, of course, the piece where you have weight 1 in every slot, which I denote by delta 1, 1. Okay? Yeah, I just don't want to write down the others. That's the point. And so, well, if you look at this delta 1, 1, then you have here are the two terms. So the dialog gives you minus log 1 minus x tensor log x, while the product of two logs just gives you the symmetric combination of the two tensors. And now, I guess you can easily see that the first term cancels. This term cancels this term. So you're just left with the second. So you see that at the level of the coaction, you actually see that these two terms that you had at the beginning up here actually cancel out partially. There's just one term that's left over. Note that here, this is actually the same as what you would happen at the level of the symbol. And what is this thing that is left over? Well, you can easily see that it is, and I should apologize. This is actually, I made a mistake here. This is like this. So it should be log x, not log dialog 1 minus x. I apologize. Here it should be 1 minus x. So what you see is that this thing, these two are the same, except that you have to exchange x and 1 minus x and the sign. But this violet thing came from a dialog. So this guy will also be a dialog. The only difference being that I have to exchange x and 1 minus x. Okay? So now you see that after I actually use the coaction, I see that these two terms are actually just a single term. Also here, everywhere, I used the wrong argument. Let me correct it. Dialog x, dialog 1 minus x. X, dialog 1 minus x. So what I see now is, if I compare the first line here to the last line here, I see that the first line and the last line are the same when I act with this delta 1, 1. So does this mean that the arguments of this delta 1, 1 are the same? So does it mean that this identity in green holds? No, of course not. Because just because two objects have the same image under a function does not mean they are the same. But delta is linear, so two objects are the same precisely if they differ by an element in the kernel. And the kernel here, you can easily check, is actually given by, well, it's generated by zeta 2. So the only difference is that the line in green is not true, but it is true up to something proportional to zeta 2. And now we can do what you call it as before. Well, look at special values. Once you know that the green line holds, so this green line is true, up to some multiple of zeta 2, some constant, and this constant is proportional to zeta 2. So since I need a constant, I can just put in a constant value for x and see what I get. In particular, if I put x equal to 1, or actually, since I made this mistake, it should be x equal to 0. If I put x equal to 0, I get that, well, and again, here also should exchange it. I apologize. And also in the final equation. So we put x equal to 0, then L2 of x is just zeta 2. So no. Okay, so it's 1. Let me just check that I corrected things in the right way. So, right, if I put x equal to 1, L2 of x gives me zeta 2. The second term, 0. L2 of 1 minus 1 is 0. So my constant, my unknown constant is actually just zeta 2. And so this last line is a valid equality. You can check it. You even find in Google is a very well-known identity. In this case, actually, I wouldn't have needed all this fancy mathematics. This is an identity that has been known for 300 years. But you can imagine if you have more complicated expressions, then things, well, you cannot find these relations on Wikipedia anymore, but you need more complicated mathematics. And that just to give you an idea, yeah?
Excuse me. So I have a naive question. So what happened to log 0?
Yeah, so when I put x equal to 0, so you say, but log x blows up. Yes,
Right.
but so the limit when x goes to 0 of log 1 minus x log x, this is 0.
I see. Okay, thanks.
Yeah, but a good point. That's a good point. The 0 that you see there is, of course, log x blows up, but it's multiplied by 0. So why do we care? Well, to give you an example is, well, almost classic by now. If you compute the 6.2 loop remainder function in planar n equals super Young Mills, if you don't know what the remainder function is, it's not so important. This is 6.2 loop amplitude. You can do it. You just compute all the integrals. I'm not going to tell you how you do it, but you can do it. You can evaluate all the integrals. And you get 17 pages of polylogs. Now, if you, in principle, there's nothing you can do with it. But then Mark Spradlin, whom you know, who gave the lectures before, and his collaborators, they showed that, well, that was the first time the symbol was used in physics, that these 17 pages can be written in one line. And so it's not just about finding little identities among polylogs, it's really that by using this technology, you can really dramatically simplify certain expressions. Like, for example, this remainder function was simplified from 17 pages down to one line. And if you want to understand the structure of the function, of course, if you have 17 pages, it's very hard. If you have one line, then there's something you can do. So this is very useful if you manage to simplify expressions in this way. However, it's not just for the beauty of it, right? It's, yes, simplifying things from 17 pages to one line is, of course, nice, but you could say, well, if I care about making predictions for experiment, I don't care too much about things being nice, I care about the number that comes out. So whether I can fit it in a line or not is a bit immaterial. But even then, you care about simplifying these things, because if you have to get a number out, you have to evaluate this thing numerically. And you do not just have to evaluate it numerically once, you have to evaluate it numerically 1,000,000 times, for example, because these amplitudes are still inserted into integrals, into phase space integrals. So they are just, once you know the amplitudes, that's just the beginning in some sense, because then you still have to do other integrals on top that you have to do numerically. And if you have to evaluate numerically a function 1,000,000 times that is 17 pages or one line, that does make a huge difference. Okay? So understanding these relations among these functions is very important, both for formal reasons and for formal studies of scattering amplitudes, like studying amplitudes and integrals for super Young Mills, but also for practical applications where you have to optimize the numerical codes. And the mathematics that you use is essentially the same. And the mathematics that you use, you can trace it back to what we said in the first part of the lecture, that you have this polylogs, you have these special functions, you have this coaction, which allows you to derive these identities. Okay? So this was just to give you a flavor of how this works. But there's a lot of literature out there on how to simplify polylog expressions using symbols, so I invite you to look at that. I also sent to the organizers some references to some lecture notes where you find more worked examples in that direction. Other questions? Okay. So then let's move on in our application of all this mathematics to amplitudes. So, and well, so far we've only looked at polylogs and all this mathematics for polylogs. So at this point, I have to make a restriction. I should say that from now on, when I say amplitude, I always mean amplitudes that can be expressed in terms of polylogs and possibly even simpler functions, rational functions, and algebraic functions. Like this 3-point function, this triangle that we had at the very beginning of the lecture on Monday, which was expressed in terms of rational functions and dilogarithms. So from now on, I will only focus on those amplitudes, because those are the ones we understand well. So what can we say? Imagine you have an amplitude that can be expressed in terms of polygons. What can you say about it? Well, the first thing that is known in terms of conjecture, if you have an amplitude with L loops in 4 space-time dimensions, and if you can write it in terms of polylogs, then the weight of these polylogs is bounded. It's not, cannot be arbitrary, but it's bounded by 2 times the number of loops. For example, remember at the beginning, we had an example of a triangle, integral, and remember that contains a dilogarithm. Here the loop number is 1, the weight is 2, which is precisely 2 times the loop number. So here the bound was even saturated. If I just show you here, it's just say dilogarithm, you can look at the exact expression and you see that the bound is saturated. The weight is 2 times the loop number. However, it's not always saturated. For example, if you look at the bubble, this will be, well, it has a pole in epsilon, but let's do not dwell on that. The finite piece is a log of, say, p squared, where p is the momentum flowing in. So here the loop number is 1. The weight is 1, which is less than 2 times the number of loops. Okay, so the weight is always bounded by twice the number of loops, if you can write your amplitudes in terms of polylogs. So if it's a 1 loop amplitude, the weight can be at most 2. And remember that we said 1 loop amplitudes can always be expressed in terms of dilogarithms, which indeed have weight 2. That is part of, well, consequence of the conjecture. You can say the conjecture builds as an extension of that. That 1 loop you can have at most weight 2 dilogarithms, 2 loops you can have at most weight 4, and so on and so forth. Okay. So that is conjecture, but so far it's what it is, right? So what else can we say? Can we say a bit more? So let's say I have an amplitude A and test L loops. Okay, but what can I do? Let's act with the coaction. Right? So A is a function in terms of polylogs. So A is made out of polylogs. And I act with the coaction. It acts on the polylogs, and I can write it schematically as like L tensor R. There's a sum of terms, and there's a left factor and a right factor. Fine. So what can I say about L and R? Well, what we did say is that discontinuities always only act in the first entry. So if I take the discontinuity of an amplitude and act with the coaction, I get the same as this expression in red, except that I have to take the discontinuity of L, not of R, only of L. Because discontinuities only act in the first factor. But now remember, discontinuities of amplitudes, that is something that has physical meaning. That is unitarity. The discontinuities of an amplitude are described by unitarity. So you can, in some sense, say that unitarity is encoded in the first entry of the coaction, because that is where the discontinuities act. So this is something that is, in the literature, goes under several names. Sometimes it's called the first entry condition. And then there's something slightly more general than the first entry condition. So first entry condition is usually what people call it only when they talk about the symbol, but it's essentially what I just described. Another name that shows up in the literature is the cosmic Galois principle. The cosmic Galois principle is even a bit more than what I described here, but what I said here is kind of the weakest version of what is called the cosmic Galois principle. You can say the cosmic Galois principle says that the unitarity is encoded in the first entry of the coaction. That is one, well, it would be one consequence of what is called the cosmic Galois principle, which is a bit more general. So we've learned already something new. So now we have this coaction, which was actually a purely mathematical object, right? It had nothing to do with amplitudes a priori. There were these polylogs, and we studied their properties, and we defined this coaction, which had nothing to do with physics. But now we see that actually this coaction sometimes knows about physics, because it knows about unitarity. Okay. But you can still say, why do I care, right? There's still so far I've not calculated much, right? I just said the coaction codes unitarity. But let's look at some more specific theories. So if I take a random quantum field theory, I wouldn't know much more to say. But let's look at special theories. So we usually are interested in special theories, like n equals for super Young Mills. In n equals for super Young Mills, people have observed that there was this bound on the weight. We said that at L loops, the weight is bounded by 2L. And in n equals for super Young Mills, for some reason, this bound is saturated. N equals for super Young Mills saturates this bound. So in n equals for super Young Mills, an L loop amplitude only involves functions of weight 2L. Okay, so that's a very strong statement. So n equals to super Young Mills at L loops has weight 2L. There's a caveat, I put it in brackets, if the amplitude can be expressed in terms of polylogs. So let's look at an example maybe. For example, the one loop 4-point function n equals for planar n equals for super Young Mills. So this is planar n equals 4-point is actually at one loop, the 4-point amplitude is given by 3 amplitude. Let's call it 3 times S times T times a box integral, a scalar box integral. And if you look up what this function is, there's a 1 over epsilon square pole. I write it schematically, I don't write the exact expression. There's a 1 over epsilon, which looks like this. And then there's a coefficient, an overall numerical coefficient that I forgot. And then there's the finite term, again, up to overall numerical coefficients, looks like this. Again, there's probably some numerical coefficient here. And what you see is that, so let's first look at the finite term. the finite term, this term has weight 2, the log square. And also this term has weight 2. So the weight of the finite term is 2, which is precisely 2 times the loop number. We were at one loop. So then there are these poles, which are infrared poles. But what you see is, so there's this term is weight 1, this term is weight 1. So if the weight of epsilon is -1, so that the weight of 1 over epsilon is +1, then also this term has weight 2, and also this term has weight 2. So you see that indeed the 4-point amplitude at one loop in n equals super Young-Mills only has terms of weight 2. If you were to compute this amplitude in QCD, for example, you would have terms of weight 2, weight 0, and weight 1. In n equals 4, you saturate the bound and you only have terms of weight 2. Okay. So, more concretely, in n equals 4 super Young-Mills, if you have an n loop amplitude, so I have now an L loop amplitude in n equals 4 super Young-Mills. Since it saturates the bound, and if it can be expressed in terms of polylogs, you can always write it in the following form. So it's a sum of terms of some transcendental functions, which are actually pure functions of weight 2L. Pure function is a concept that we had defined some 20 minutes ago, which says that the derivative of this function only involves pure functions of weight 1 less and d logs. So an L loop amplitude in n equals 4 super Young-Mills is a sum of terms which are pure functions of weight 2L multiplied by algebraic functions. So if you go back to the example that I just gave you, here the one loop amplitude 4 points, you can write it as R times T. There's only one term, so it's R1 T1 if you want, where there is a transcendental function, which is this box integral, which has weight 2. The weight here is 2. So it saturates the bound. And then there is a rational function, which is the 3 amplitude that multiplies it. Okay? And similar structures hold for every amplitude in n equals to super Young-Mills, even if you look at non-planar corrections. Okay. So now we've learned already something about the structure of this specific theory. So, still I haven't computed much. But with what we've learned now about the structure about these amplitudes n equals to super Young-Mills, we can now go and try to use it to do something new. And this is something that you may have heard of as the Bootstrap program. This is not what is sometimes called the conformal bootstrap. This is the something called the hexagon bootstrap. Of course, mostly pioneered by Lance Dixon and his collaborators. And well, I focus from now on the planar limit. So I've used the word planar limit already many times, but maybe let me give you the definition just so we all agree on what it means, because now we're actually going to work with it. The planar limit of an SUN gauge theory, this looks like SON, I mean SUN. The planar limit of an SUN gauge theory is the limit where n goes to infinity, the number of colors is very large, but g squared times n is fixed. So g squared is the coupling constant. And why is this limit, where the number of colors is very large, called the planar limit? Well, that is because you can actually prove that if you take this limit where n is very large and g square n is fixed, only planar Feynman diagrams contribute. So just for make sure everybody's on the same page, what does it mean, planar? Planar means that you can embed the graph on a plane without lines crossing. For example, this graph is planar. Why is it planar? Well, to see that, add a point, and you can see that you can connect all the external lines to this point, and there's no lines that cross. Diagram that is not planar would be this one. Why? Because now if I add a point, so for these four, I can connect everything to this point without lines crossing, but here you see I'm in trouble. Here I would need to cross a line. So this graph is non-planar. And you can show that in the planar limit, which is n to infinity, g square n fixed, only planar Feynman diagrams contribute. So you have fewer diagrams, which is good. And it's simple. And well, I won't have time here to talk about all the properties of planar analytics and super MPLs. That would be a whole lecture on its own. Here I just say, well, there are, in the planar limit, the theory develops new symmetries, which are very strong and which essentially fix many parts of the amplitude. And what I will talk about here is, well, the word I already used, which is this remainder function, which is essentially what I mean by the remainder function for an endpoint amplitude. So n here, n is number of external particles. The remainder function for n particles, I define it as the scattering amplitudes divided by some other quantity, which I call BDS, doesn't matter what that is. Actually, I wrote it. Okay. Such that, well, each of the numerator and the denominator is divergent, but the ratio is finite. So it's what I'm going to look at is essentially ratios of amplitudes that are finite. That's, you can describe it that way. And they will be normalized in such a way that, well, at tree level, so the leading order, tree level, is 1. You can also normalize in such a way that the one loop is 0 in the ratio. And so the first non-trivial piece is at 2 loops. So I'm not going to explain where this comes from. This would be a whole lecture on its own, just to say that the quantities that I want to compute are these ratios. So what do we know about these ratios? Well, we already said you can actually choose them in such a way that at one loop they all vanish. So all these ratios at one loop are 0. And you can also prove, this is non-trivial, that these ratios vanish at all loops for 4 and 5 particles. So the first time this ratio is non-zero is for 6 particles and 2 loops. And the conjecture is, if you look at MHV amplitudes, those are pure functions of weight 2L. So it's saturated bounds, and they are pure. I remind you, because I guess MHV, the concept of MHV amplitude is probably something you've either heard before or maybe in Mark's lecture, Mark's Bradley's lecture. MHV means that the helicities of the external gluons, I'm looking, for example, at external gluons, so yes? So the helicities of the external gluons are such that two gluons have a negative helicity and all the others have a positive helicity. That is what I call an MHV amplitude. MHV stands for maximally helicity violating. Why two negative helicities and the rest plus? Why not all plus? Well, you can show that in the supersymmetric theory, and n equals to supermills is supersymmetric, the case of all plus or one minus and the rest plus vanish. So the first case that is non-vanishing is two minuses and the rest plus. So it's the simplest possible helicity architecture. And those are conjectured to be pure functions of weight 2L. Okay, fine. Why do I care? Well, let's go and combine everything we know. And that is what leads to the Bootstrap program. So, if I say that these MHV amplitudes, these remainders, are pure functions of weight 2L, well, what does it mean? Well, I can now compute a symbol. The symbol of a pure function of weight 2L has 2L entries, right? So if I also tell you what the entries in the symbol are, the entries in the symbol are sometimes called letters. The entries in the symbol, I mean, we called the symbol before like A1 tensor A2 tensor A3. I mean, this A1, A2, A3, I would call them the letters. So if I also tell you what the letters are, you know that, well, you could try to write down the symbol for this amplitude. So the basic idea, you can structure this, the Bootstrap program, you can say it as follows. Since, let's only discuss the case of MHV amplitudes. You could try to do the same for other holistic configurations, but let's only focus on MHV for the sake of the lecture. So if MHV amplitudes are pure functions, they're already very constrained. They are pure functions of weight 2L. So try to write down the unique possible function that you can imagine that has the correct analytic structure. Well, what could this function be? Well, one thing you know about it is that if you look at the symbol, if I somehow tell you what the letters of the symbol could be, you could try to write down a symbol, at least for the amplitude. Now, of course, you would need to know what the letters are. For the two-loop, for the 6-point amplitude, it turns out that the two-loop 6-point amplitude symbol involves 9 letters. That is 2 loops. So now you can possibly say, well, maybe those same 9 letters are sufficient at any loop order. So if I tell you then that, say, the 3-loop 6-point amplitude is now a weight 6 function, if you make the hypothesis that its symbol has the same, involves the same letters as the 2 loops, you could write down the most general symbol you could possibly imagine, and then try to impose constraints on it to see if you get a unique answer. Of course, there's a big caveat still, because I made the assumption that the letters at 3 loops are the same as the letters at 2 loops. However, there's strong evidence that, at least for the case of the 6-point amplitude, it's the same 9 letters that appear at all loop orders. There are various ways of arguing this. I'm not going through that, but essentially we said that the symbols are kind of invariants attached to polylogs. Well, And the letters are, if you want, the building blocks out of which you build this invariant. Well, you know the letters for the 6-point amplitude in planar n equals to super young Mills, so you could try to build a symbol, just basic invariant. Let's for now only focus on the 6-point amplitude. We will come back to more particles later. So, said differently, I could try the following. So I'm looking for a pure function of weight 2L. Let's say weight n, just to fix the idea. And I tell you that the symbol of this, so let's try to construct the most general function. The symbol has letters only from this 9-letter set that I observed at 2 loops. But I know a bit more. I mean, I can write down many functions that have this property, that have a symbol of this type. I know more. Because I also know that if I act with the coaction, beside the coaction encodes unitarity. And my amplitude clearly must satisfy unitarity. So if I can write down a set of functions that have the correct invariant, the correct symbol, correct invariant to characterize them, and then I can use the coaction, which encodes unitarity in a certain way, to constrain that most general answers I could have. What this tells me to some extent is that since the coaction encodes unitarity, and the coaction also relates functions of different weights, it means that the functions of different weights that I construct in this way are not independent. So I can, if I know the correct set of functions for weight 2 that describe a 1-loop amplitude, weight 2 means 1 loop, I can try to construct the correct set of functions that describes 2-loop amplitudes. I can construct the correct set of functions that can describe 3-loop amplitudes, and so on. So more formally, for example, I could construct a set of functions that satisfy this condition C1, which is having the right type of symbol. And I could construct another space of functions which satisfies 1 and 2. And they're all pure functions of weight n. I guess you can clearly see that the functions from Vn are a subset of those of Vn tilde, because Vn tilde only satisfies condition 1, while Vn satisfies condition 1 and 2. So if I take a function from Vn, which is a function that could be an amplitude, it has the right properties to satisfy unitarity, and they act with the coaction, then, well, the coaction, since it encodes unitarity, must have a function from the correct space Vn also in the first entry again. While the second entry can be more general. And so you see that these functions that satisfy unitarity, they are related to the coproduct, to the coaction. And you can use that to actually construct these functions, because if you know a set of functions with the correct behavior so that you can satisfy unitarity, you can use it to construct a basis of functions at the next weight. I should mention here, I only talk here about unitarity and first entry condition. There's a bit more. There are these what's called Steinman relations. I'm not going there. You can go to literature and check that. So here it is just a bit more. So I can imagine that if you have a basis of your space Vn, B is a basis for that space at weight n. B tilde is the basis for V tilde. The idea is if you know the basis up to some weight n, well, how can you find the basis for weight n plus 1? Well, write down the most general function. And since Vn is contained in V tilde n. You write down the most general combination of functions of V tilde n, and you require that they satisfy the property when you act with the coaction. They must be such that they satisfy the first-entry condition. So you actually get a linear algebra problem that allows you to determine a basis of functions that satisfy unitarity, whatever that means, but that's the basic idea. And so if you have a basis of functions that are compatible with unitarity, well, then you know that your amplitude must live in that space. And you know that since the amplitude is a pure function of weight 2L, the coefficients in these linear combinations, they must be constant. That's what it means to be pure. So being pure means that your coefficients are just constants. So if you have a basis for the space of functions that are compatible with unitarity, you can write down the answers for the amplitude. So how can you determine the coefficients? Well, there you have now to put in some physics. There you have to, some physics also in the sense of you have to put in that you are in the right theory, for example, n equals 4 super MPLs. But you can do that, for example, by looking at limits. For example, you look at collinear limits or other kind of limits, high energy limits. And it turns out that that determines the amplitudes uniquely. So using this, there was a whole program, as I said, mostly led by Lance Tix and his collaborators, to determine, well, they have managed to determine the 6-point amplitude through 7 loops. And that is quite crazy. I mean, usually in QCD, you wouldn't even know how to compute the, well, right now, we still stuck at n equals 5 at 2 loops. While in planar of super MPLs, using this Bootstrap program, people have gone to 7 loops. And for 7-point particles, you can do essentially the same, and you get to 4 loops. People have managed to go to 4 loops. For n greater 7, it's more complicated. There was recent work also by Song and his collaborators about that. There the question is already what is the correct set of letters. You wouldn't know a priori. Right now, in the last couple of weeks and months, people have started to understand how to get a set of letters beyond 7 points. That is the basic ingredient you need. But I don't think there's a definite answer yet. And also, I think it's not clear that beyond 7 points, you know if MHD amplitudes are polylogs for any number of legs and any number of loops. It's actually also not clear. While for 7 external particles, there's very strong evidence that all MHD amplitudes are polylogs and that the letters that you get are the same at every loop order. Okay. So that is all I wanted to say, I think. So if you still have questions, we still have 10 minutes. Feel free to ask as many questions as you like. And I hope you enjoyed the lectures and you learned something.
May I ask a question?
Thank you very much. Yeah, go ahead.
Yeah, do these polylogs also appear in n equal to 8 supergravity?
Yeah, of course. I mean, if you evaluate the amplitudes in n equals 8 supergravity, that's what you get. For example, well, people usually only look at integrands in n equals 8 supergravity. Only very few amplitudes have actually been evaluated. But people have evaluated 2-loop amplitude for 4 points and 5 points, and 3-loop amplitudes for 4 points, and you get polylogs. And actually, also n equals 8 supergravity is another theory that seems to saturate this bound. So also in n equals 8 supergravity, it seems that at L loops you get polylogs of weight 2L, assuming that the amplitude is polylogs.
Okay, thank you.
Hi, Claude. If you look at the triangle loop that you discussed before, which is a dialogue,
Yeah.
And then if you apply the coaction and you get this non-trivial term log 1 minus x and log x, right? So is there a Feynman diagrammatic representation of this this coaction, the right hand side?
Yes, there is. I can show it to you. Here, you're talking about this expression here, right?
Right, yeah.
So let's take this. So, what would happen if you go and you compute the coaction of this? Yeah, that's what you want to do, right?
Yeah.
What you actually get, that's very interesting, is the following. So you get, so here you have P1, P2, P3 as external legs. You get the following. You get one term looks like this. But here you have to cut. And then you have three more terms. So you get three more terms. They all look the same, except that it's a different momentum. And that they correspond to, on the other side, you have the three cuts that correspond to the momentum that is in the first entry. So yes, the collection there has an interpretation in terms of Feynman diagrams. And what you see there is, so I insisted that the collection codes in entirety.
Yes.
You see it here. You see here that the first entry here is always a Feynman diagram itself.
Right.
So it always satisfies in entirety because it's a Feynman diagram. So that is a manifestation, if you want, of this, that delta disk equals disk only the first entry, right? We wrote like this. This is a manifestation of that. Then there was the question that was asked earlier in the lecture, said, what about this? Is this somehow related to cuts? Well, you see now that the second entries, they are the same graph, just different cuts of the same graph that I had originally. But all these integrals that are in purple satisfy the same differential equation because they're always triangle graphs. They correspond to different cuts, but cuts satisfy the same differential equations as the Feynman integrals themselves. So therefore, that is what is encoded here. The fact that derivatives only act in the second entry tells you that the second entries can only be the same graph, possibly with different cuts.
Right. So from this perspective, is there an understanding of the symbol? So when you do coaction and you finally go to the 1-1-1 decomposition, is that related to cuts somehow?
Yeah. So here it's a bit trivial because you see this is a way two functions, so the symbol is actually the same as this.
Yeah, right.
So here there's not much to do.
Right.
Now, if you were to go to weight 3 function, for example, this would be weight 3 in 6 dimensions. So the symbol would have a structure as follows. So the first entry would always be a bubble of either one external moment, so of some invariant attached to this 6-point function. The next entry would be some cuts of this, would be a cut of a 4-point function where the channel that you cut, so if this is p squared, then the momentum flowing in this, so this invariant would be p squared.
Mhm.
And then the last guy would be some kind of double cut of a hexagon, such that if you, well, let's maybe write it like this, where the red, if you remove the green lines, you get the same as this cut.
I see.
This, for those who know what it is, this would be a manifestation of Steinman or extended Steinman. This is a bit speculation, but that's what it should mean. That you can only have these cuts in a certain nested way.
Right.
Okay.
So what if you had a diagram which had like an overlapping divergence, for example, like a two loop? Is there some issue with coaction, or is it if still is okay?
Well, so the correct, I didn't discuss divergences, but it works out in a non-trivial way. For example, even you don't have to go to overlapping divergences. Even here, this guy is finite.
Yes.
This is divergent.
Yes.
So actually, all of these terms are divergent. 1 over epsilon. Here's simple divergences, right? They're not overlapping.
Right.
Now, what happens? Well, what happens is that these cuts that go with it, so if you compute this guy, this plus this plus this, you can actually prove this is order epsilon.
Mm-hmm.
So there's 1 over epsilon from each bubble, but
right.
It's like if the cuts know about the divergences that are in the integrals on the other side.
Right, right.
So it all works out in the end, but it's highly non-trivial, right? That there's
so intuitively, can I think of coaction as subtracting divergent subgraph somehow, or is it?
No. That is what, if you were familiar with, there's another coaction on a co-product on graphs, which is
yeah, that's an older one, the Hoff, the Kramer-Kunz.
Exactly, that is the one that extracts subdivergences.
Right.
However, that one does not correspond to the so the non-trivial thing is that this expression here, which is graphs and cut graphs, is the same as if I had acted with the co-product on the polylogs on every single polylog in this expression.
Okay.
But that co-product on polylogs didn't know anything about Feynman integrals.
Yes.
So the fact that this co-product on polylogs, which has nothing to do with Feynman integrals,
right,
knows about all of these properties of graphs and Feynman graphs and their cuts, is a highly non-trivial thing.
Right.
Now, the Kunz-Kramer is also a co-product on graph, but it would not have the property that it reproduces the co-product on the polylogs if you replace the graphs by the analytic expression.
Right.
So it's not that one is wrong and the other one is right. They're just different objects.
Different, yeah. Thanks.
So there's someone asks on the chat, is there a translation of previous diagrammatic representation of coaction in terms of Discontinuities polynomials? It's a very good question. I don't know. Because the coaction is a statement about integrated functions, about integrals. The semantic polynomials, so for those of you who don't know what semantic polynomials are, it's the integrand of the Feynman parameter representation of the Feynman integral. So the semantic polynomials are the integrand of something. I don't know at this point how you translate one into the, how you make the statements about the coaction, which is a statement about the integrals, into a statement about the integrands. But it's a very good question, but I don't know the answer.
Hi, Claude. Can you say a few words about what we know about functions beyond multi-polylogs?
Yeah, so here I've only covered polylogs because that already takes a lot of time. Now, not every function can be expressed in terms of polylogs. The simplest example of something that's not a polylog is this simple two-point function where you have masses here. And what happens is that this guy evaluates to, well, if you look at the cut evaluates to something called an elliptic integral. Now, an elliptic integral is, well, I give you the basic definition. It's an integral of this type. So you can see from this integral definition, this looks very different from the definition of a polylog. And you can actually prove that this guy is not contained inside polylogs. This you can prove mathematically. There's no doubt. So now if you look at the full integral, not just the cuts, well, you know from quantum field theory that an integral, you can always write it as some dispersion type integral of the cut. So this integral will be, this integral here, will be an integral over this elliptic integral. Okay, schematically. So that thing will never be a polylog. So this integral is the simplest example. It will never be a polylog. What you get, however, is you get generalizations of polylogs. And the story goes as follows. So polylogs were defined by looking at differentials of this type. You should think of this as you have the Riemann sphere and there was a pole at t equals a. And t is a coordinate on this sphere. And what you do is this, you integrate along some path and you have these differential forms that have poles somewhere. So this is the Riemann sphere. So it has genus 0. Now, what happens is you can go on. You can go, for example, and consider a Riemann surface of genus 1. You could now look at functions that have poles on there. And you could integrate along some path. That would be an elliptic. This would give you a polylog. This would give you an elliptic polylog. So it's the natural generalization. It's a generalization of this idea of integrating differential forms with logarithmic singularities along a path from genus 0 to genus 1. That gives you elliptic polylogs. The main difference is, and that is where all the complexity starts, that you know, well, this is now maybe a bit for the experts, you know that if you have the Riemann sphere, if you have genus 0, you only have differentials with logarithmic singularities, while if you go beyond genus 0, you also have what is called holomorphic differentials. Which in the case of genus 1 surface are precisely objects of the type dt over square root of something like this. Not exactly this, but something like this. But that is precisely why we had here this object. So you get these new objects precisely because you have, if you want a non-trivial topology where you have other things than just logarithmic differentials. But the idea is exactly the same. You would need to look at what are the kind of differentials that are associated with your geometry, and those are the class of functions that you get. It's just that genus 0 is very simple. Then beyond that, you could even go on. You could now either look at higher genus, or you could look at more complicated geometries like Calabi-Yau surfaces. We could still play the same game, but it becomes infinitely complicated, at least for nowadays. Maybe things change as technology evolves, but the knowledge now is that to go beyond genus 1 is very complicated.
Is there a relation between what surfaces the Feynman variables live and these momentum variables live?
Can you repeat your question?
Is there a similar understanding of on what kind of surfaces the Feynman parameters live when you similarly write the integrals?
Well, the Feynman parameter integrals, they are not integrals along a path, right? Here, so polylogs are obtained by integrating along a path. Elliptic polylogs as well. Feynman parameter integrals usually are integrals over symmetries. How you go from one to the other is not obvious. So reading off the geometry or the class of functions from the Feynman parameter integral can be done in principle, but it's very, very tough. I don't know if that answers your question.
Okay, thank you.
And there's also certain generalization of the idea of coproduct now for the elliptic multi-polylog and so on, right?
So the coproduct, you can define it in principle on everything. On everything that comes from geometry, if you want. Those are these motivic, you get these motivic periods, and they always come with a motivic coaction. Those are very abstract constructions, and to write down formulas can be very tough. So the answer is yes, in principle you can do all that, but if you want to do it in practice or use it in practice, that can be very complicated. For polylogs, we are lucky that it's simple enough that you can write down everything explicitly.
Okay, are there more questions? Could you also say very briefly the perspective of using this bootstrap idea for other variables or in other theories? Since you mainly talk about hexagon in n equals 4, right?
So people are thinking of doing the same kind of bootstrap ideas for other theories, but it's gets very complicated, and for two reasons. So first reason is this. So n equals 4 saturates the bound, and they are pure functions. So you have this ansatz down here, which is not true in general theories. In general theories, you could have, well, you have an upper bound on the weight, but that's it. So the ansatz that you get is much, much larger, especially since you don't know exactly what kind of algebraic functions you need.
Right.
Then you wouldn't need what are the letters. So the other thing that saves you is that here you have this idea that you kind of, for 6 and 7 particles, you know what are the letters. So for general cases, you wouldn't know what the letters are. And then on top of that, even if you knew the letters and you knew what to do with the fact that it's not a pure function, you would need to physics constraints. And n equals 4, we know a lot of constraints on integrability because we know that in certain limits, the theory must behave in a certain way to all orders in perturbation theory. We have a lot of input from integrability about what you can use as boundary data to constrain the function, which in QCD you wouldn't have. You would probably know that in the collinear limit, it must have a certain behavior, but that's like one constraint, and you would need thousands.
Okay.
So we're still far from bootstrapping real theories, but yeah, things may change.
Okay, thanks. Any other questions?
Hello? Hello.
Yeah.
Can you hear me?
Yeah.
Yes.
Yeah.
Okay, so I have a kind of a naive question. Is it possible to write down a sort of a simple quantum field theory by using a collection of polylogs, so that all the amplitudes are written in terms of these polylogs and they automatically satisfy all unitarity conditions, without even talking about the Lagrangian and so on?
I don't know. I don't know,
Is
because
that a reasonable question?
I don't know, because you see already in theories as simple as lambda plus 2, polylogs are not enough. So,
So I mean, so we should probably cut the.
We know the polylogs are not enough at some point in perturbation theory. So that does not mean that what you suggest cannot be done. But my first question would be, you would need to find a theory in which you know that polylogs are enough to all loop orders, which seems tough, but maybe it can be done. There may be a chance in certain two-dimensional theories, but I'm not sure.
Thank you.
Okay, if not, let's thank Claude for all these wonderful lectures.